Okay, so the time's up. Um, so we'll start. Hey everyone, good morning. Today we will continue with flows, but now pipes have costs. So for now, the definition of the flow is the same. So the flow is a function that takes an edge. So yesterday, if there were multiple edges between two vertices, so for example, if there was a pipe with capacity 5, pipe with capacity 3, and pipe with capacity 7, we could replace that with a single pipe with capacity 15. Right? So it doesn't matter which pipe we use. So we can just say that this is a single pipe with capacity 15. Now, different pipes can have different costs. So, for example, a cost of pushing 1 unit of flow along the first pipe might be low, along the second pipe might be high, and along the third pipe can be somewhere in between. For example, this will denote that as 5,1. This means that we can push 5 units of flow, each costs 1. Or we can push 3 units of flow, each costs 5. Or we can push 7 units of flow, each one costs 4. Now, as you see, we cannot just erase multiple edges into one, since they will have different costs. So now we'll have to define the flow function a little bit differently. So for each edge, we define an integer number, as before. And all those properties are still there. So flow is antisymmetrical. I don't remember the order I introduced last time. Okay, so first one is a capacity. First one is a capacity constraint. So still we have an upper bound on how much flow we can have along this pipe. Second one is antisymmetry. So F, well, let's say for an edge UV should be minus F VU. Well, now it's not entirely clear, right? So before we had just two vertices, and sometimes there was no edge, but we could still have a negative flow. So for example, if there was only one edge in this direction from U to V, and we had 3 units of flow out of 5, then basically in the residual network, we had a capacity 3 edge back. So, or it's the same as we have minus 3 units of flow out of 0. So we'll change this definition for edges. So F flow for each edge should not exceed the capacity of this edge. So let me change this a bit. F of E should be smaller than C of E. And F of E should be minus F of E asterisk. Let me explain what this is. And again, all outgoing flow for each vertex except the starting vertex and the ending vertex is 0. So sum for all UV in our graph, F of UV should be 0. So U fixed for fixed Q that's not S or T. Okay, so what is this new edge? So when we consider reversed edges, sometimes the reverse edge does not exist. So for example, in this case, if we only have one edge in direction from U to V, well, there it is, and there is no reverse edge. So if there is no reverse edge, so if our graph is undirected, we should create a fake reversed edge. So we create a back edge with capacity 0, and, well, initially flow is 0, but whenever we add some flow along this edge, we will subtract the flow along this edge. So if this becomes 3, this will become -3. So this is one detail that I didn't explicitly mention yesterday, so that we have to create reversed edges if there are no reversed edges. So that for each edge, we have another edge that goes in reverse. So that when we add some flow along some edge, we have to subtract the flow along the reversed edge. The same will be here, but we have one more parameter, and it's a cost. Let's call it W of E is the cost. So each edge now has a capacity and a cost. So now we can define what is the cost of the flow. The cost of the flow, W of F, is, well, for each edge where there is a flow, we multiply the flow times the cost of transporting 1 unit of flow. So it's sum for over all edges E in our graph, where the flow along that edge is positive, F of E times W of E. K, where K is some constant or somehow may be defined in the problem statement. And the third one, about reversed edges, what do we do when we introduce reversed edges? Well, if you remember, introducing a reversed edge just meant that we can cancel the flow in the opposite direction. So pushing the flow along this edge is the same as pushing the flow along this edge with capacity 0 and current flow is -3, is the same as canceling these 3 units of flow along the opposite edge. Well, now we have two parameters. For example, we have some capacity and some cost. Well, what should reverse edge look like? Well, the reverse edge should look like, well, capacity is still 0, so it's just there to cancel the flow along the reversed edge. But what should be the cost? Yes. So pushing 1 unit of flow along the reversed edge is canceling the 1 unit of flow that goes through this edge. So the cost of that is -W. So we cancel, and the costs can be negative. It's fine. Well, it's not fine since this introduces a problem that we will be solving today. Is that what is the best algorithm to finding the min cost max flow? And since there are negative edges and we will be finding shortest paths, we cannot use Dijkstra's algorithm easily, but we will. Okay, by the way, the same formula can be rewritten without this restriction now. So for now, let's just believe me that the circulation can be represented as a union of paths. This cost function is additive. This means that if we add two flows, their costs are added. So this is a linear function on the values of f. So we just, if we consider f minus f min, the cost of that is the difference of two costs. So should do the other way, right? So f min minus f. So f min minus f is negative. Since this is smaller than this. So this is negative, but this is represented as a set of cycles. And it's a common technique to prove that something is not maximum or it's not minimum. For example, if you know matchings, this is the way to prove that the matching is maximum if and only if there are no augmenting paths, right? So you take the difference between two matchings and it's decomposed into cycles and paths. So here it's a little bit more general. So this is the union of cycles. And the total cost is negative. So this means there is at least one negative cycle, which is a contradiction. So now, this gives us an easy, but not good so far, an easy algorithm to finding the minimum cost flow. Right? So this tells us that if we keep removing negative cycles from the residual network, this will result in the minimum cost flow sometime. Well, we don't know how many cycles we need to find before we arrive to the situation where there is no negative cycle at all. Yes?
Do these union of cycles join edges too, or just vertex?
Excuse me? So there is this is the union of cycles. Well, what is the flow, right? So the flow is a function for each edge. So for example, here we can have 2, 4, 2, 4, 2, 4. So this can be represented as a union of two cycles. This one with capacity 2, and this one also with capacity 2. Right? So when I said that some flow or some circulation can be represented as a union of cycles and maybe paths, this means that it can be represented as a sum of flow functions. Each one is just a path, or each one is just a cycle. Is it clear? Okay. Well, I'll tell more about it in a minute. So the easiest algorithm, well, to describe, not the one to code. So the algorithm looks like this. Let's forget about costs and find the maximum flow or any flow of some fixed size. This cannot solve the third problem yet. So algorithm for problems 1 and 2. First, find any flow, the maximum one or sum of the fixed size, and then keep augmenting negative cycles. So we take our residual network, we find any negative cycle, we push the minimum residual capacity through it. Again, we build the new residual network, we find the negative cycle, we do it again. So this is similar to Ford-Fulkerson algorithm, right? So we just took the theorem and based an algorithm on it. Sadly, again, in the worst case, it's not polynomial. So in the worst case, you'll have to cancel a lot of negative cycles to achieve the situation where you don't have negative cycles at all. Okay, so we will deal with this. I will not tell you the proofs of that the new algorithm will be a polynomial algorithm, but it's a cool trick. Don't think it works in programming contests at all. So I think just removing negative cycles is fine on its own. And the other algorithm I'll describe is even better. But for example, if you have negative cycles initially in your graph, that's the best you can do. You have to know how to find negative cycles. By the way, do you know how to find if a graph contains a negative cycle or find this cycle? Yes? No? Should I tell you about it? Okay, let's talk about finding negative cycles then. Okay, we have a graph and we would like to find out, does it have a negative cycle or not? So for example, this problem arises when we try to find shortest path, right? So if there is a negative cycle, then shortest path to some vertices just don't exist, right? So for example, we can have this kind of graph. -5, 10, -7, 1 and 2. And maybe we have another vertex here with cost 10. So for example, there is a negative cycle. So -5 plus 10 minus 7 is -2. So the total cost of this cycle is -2. And the shortest path to any of these three vertices or this vertex just doesn't exist. There is no shortest path, since for any path we can just add more of this cycle and this becomes smaller. So there is no shortest path. The shortest path doesn't exist. And if there are no negative cycles, we can show that every time all shortest paths do exist. Well, if there are no negative edges, then of course there is no negative cycle, right? So the meaningful case, if there are negative edges, and we cannot use Dijkstra's algorithm for that. So we'll have to use Bellman-Ford. So what does Bellman-Ford algorithm do? Well, it calculates shortest distances using dynamic programming. So dp of k and u is shortest, well, the length of the shortest path from some starting vertex to vertex u using k edges. Well, at most k edges or exactly k edges, doesn't matter. Depends on your implementation. Using k edges. Okay, and we know that we only should use k from 0 to n minus 1, since the shortest path cannot contain more than n minus 1 edge. Well, it can if there are negative cycles. So the way to finding a negative cycle is as follows. So we run this algorithm for k from 0 to n minus 1, and then one more time. And then once more. Basically, you can say that in this case, k is equal to n. If something changed on this last iteration, this means there is a negative cycle. Right? So if for some vertex, the shortest path to that vertex using n edges is smaller than any of the paths using n minus 1, n minus 2, n minus 3, and then up to 0, this means there is a negative cycle, and also we can find this negative cycle if we keep restoring the shortest path to that vertex. Again, the similar way you will do if you use normal Bellman-Ford algorithm. So since we have n edges in this path, we will encounter the same vertex twice. So we have n edges. This means that we will have n plus 1 vertex. We have n vertices in our graph in total. This means that we will find the repeated vertex. So we will have a cycle, and that must be the negative cycle. So it's big O of n times m. So basically, this algorithm work time is finding any flow. So for example, if we use Dinit's algorithm, this will take us n squared m. In the worst case, but as we discussed yesterday, it's really hard to build a counter case for all these flow algorithms. And the networks that you will construct in programming contests will usually be so specific that flow algorithms will work a lot faster than the theoretical runtime. So, and then we use Bellman-Ford algorithm to find the negative cycle. We can push some units of flow along this cycle, and then we'll be done. So it's the total time is, let's say, n squared m, but pretty much any flow algorithm you like, plus n times m times the number of cycles that you'll have to find. Of course, there are small optimizations. For example, we could first try to only use negative edges, right? So we might have a lot of negative edges in our graph. So what if we just find a cycle using only negative edges? Of course, this will be a negative cycle. So if we run the DFS only using negative edges, first, we'll try to find the cycle in linear time, not in n times m, but in just m. Then, if we couldn't, we just use Bellman-Ford algorithm again. So this is usually a good optimization. So this saves you a lot of time on similar problems. Okay, so this is an algorithm. Okay, so let me fulfill my promise and let's talk about flow decomposition now. Flow decomposition. We'll talk about the flow decomposition for normal flows without costs, but this transfers to flows with costs. So any flow F can be represented as a union of cycles and paths from S to T. So it can be rewritten as the sum with some coefficients AI, PI, where PI is a path from S to T. Plus BI, CI, where CI is a cycle. And all of these paths and cycles are valid in the initial graph. So this means that this is an actual path where all the capacities are positive along this path, and this is the cycle, again, where all capacities are positive. Can we only live with paths? Well, no, because we could have this kind of flow. So for example, 2 out of 2, 2 out of 3, and we can have another flow here, 1 of 2 out of 2, 1 out of 1, 1 out of 5. So for example, in this network, this is a valid flow. This upper part might seem useless, but in terms of costed flows, this can have negative cost, so we will have to use it. Doesn't have any like real life physical sense to have negative cost cycles, but sometimes we just do. So there is one path and one cycle. Maybe we could have another path that goes here. Maybe this is 3 out of 3, 1 out of 1, 1 out of 1. So in this case, there will be 2 paths. This one and this one. And this is called the flow decomposition. This is useful for proving something, but also useful in contest problems, since you would want to represent your flow as a union of paths sometimes. Sometimes the path represents something meaningful, like the path for a particular item to transfer from the source to the sink. Okay, so, and it's easy to prove. We'll prove by induction on F. And then when F becomes 0, that means that we only have cycles left, and then we can find cycles again using the same induction, but on the total sum of all flows. I think we can do it like this here too. Or sum of f of EV, f of E for all edges. This one might be easier. Okay, so if there are no flows at all, so if all flows for all edges are zeros, that means that we're done. This will be just an empty sum here and there. Otherwise, there is an non-empty edge. there is an edge somewhere in our graph that has a positive flow, f greater than 0. Well, since there is a balance property, so for all vertices except the source and the thing, the balance of outgoing flows and ingoing flows must be 0. The difference between those must be 0. And we have an outgoing edge with positive flow. This means that there must be an incoming edge with, well, at least one incoming edge with negative flow, strictly negative, less than 0. Well, I mean, like, if there is an outgoing edge of positive flow, there must be an outgoing edge of negative flow. This means that there is an incoming edge of positive flow again. Some other flow, and so on. So let's continue this process until we meet a repeated vertex. This means that we have found the cycle. Or we might reach the source. So if we reach the source, we will do the same with the end vertex of this edge. Again, we might find the cycle like this. Or we can go up to the sink. So if we didn't find the cycle going backwards or going forwards, then we found the path. And if we find the cycle, we find the cycle. And we can remove this cycle for our flow and continue. The total sum of absolute values of all flows on all edges is reduced by that. So this means that this is a finite process. We cannot do that for infinity. And that's useful for proving stuff. For example, I used it there. So a circulation does not have any path. A circulation only decomposes into the set of cycles. Okay, let's discuss another algorithm, which is a faster one, but it requires that there are no negative cycles in the initial graph. And usually that's the case, right? Usually when you construct a network for some problem, it will not have cycles even. Okay. Well, let's remember the Ford-Fulkerson or Edmonds-Karp algorithm. F or EK algorithm. Find the path until there is no path. Keep finding paths. Let's apply it here. But now our goal is to, for example, we would like to find the maximum flow with minimum cost. And our goal is to minimize the sum of all costs of the path that we would like to find. Right? So in the end, our flow is the sum of all paths that we found. So we would like to minimize the cost of all paths. Well, let's find shortest path where we only use unsaturated edges, and the cost of the edge is the cost of transporting 1 unit of flow along that edge. Let's find shortest paths. In GF. We'll keep doing that. Well, turns out this is a working algorithm that you should implement when you are working with minimum cost flows. So, just for eternity, take the residual network, find the shortest path, and push a unit of flow or push whatever you can along that path. Let's consider this sequence D1, D2, D3, D4, and so on. I'll make some claims which I will not prove today, but it's useful to know them. So let the D1 be the distance of with the length of the first shortest path that we found. So we took our initial network and found the shortest path from S to T. So this is the cost of this path. Now we pushed some flows, some edges were removed, some new reverse edges were added, and then we found D2, then we found D3, D4, and so on. Turns out that these distances are always increasing. So similar with Edmonds-Karp algorithm, where the distance to each vertex, if we run BFS, the distance to each vertex increases all the time. Here, the distance between the distance to each vertex also increases. So distance from S to X for all X increases. Well, and and the distance to the last vertex, to the sink, also increases. So this means if what we're going to find is the mean cost flow without any restriction on the flow size, the algorithm as follows. Find while true. So this is the mean cost flow without any restrictions on the flow size. So while true, P, the shortest path, from S to T in GF. If the cost of this path is negative, then we should add it to the cycle, to the flow, sorry. And if it's not, then all the paths that we will find after this point will be positive. So adding them to our flow will increase the cost. So if the cost of this path is negative, then we add it. Otherwise, we break. And the similar scheme can be used to find the maximum flow of the minimum cost. So we just keep finding paths until we cannot find one. So for example, if there is no path from S to T in the residual network, this means that our flow has the maximum. Our flow is the maximum flow. And also to find the minimum flow of some fixed capacity. So we just keep finding paths until the size of our flow reaches what we want. Okay, so how do we implement this? I had one more. Yes, this one. And the second claim I want to make is so initially there are no negative cycles, right? So I said that this is the condition for this algorithm to work. So initially there are no negative cycles. we use this property to find the shortest path, right? So if there are no negative cycles, then we can calculate the length of the shortest path for each vertex. And if there are negative cycles, that we just can't find shortest path. So if G F has no negative cycles, and P is the shortest path from S to T, and P is the shortest path S to T. If we add this path to our flow, the new residual network will still not contain negative cycles. So these are two requirements for our algorithm to work. So the length of the shortest path increase, and whenever we find the shortest path and add it to our flow, no negative cycles can appear. This means that if f prime is f plus p, then g f prime will still not have negative cycles. But basically, if the new residual network has negative cycles, again we can look at the difference between this flow and this flow, and we will show that we actually haven't found the shortest path. This one is not that hard to prove. Then G F prime doesn't have negative cycles. Okay, so these two steps, right? The lengths are increasing and no negative cycles appear. But negative edges can appear, right? So if we had some path from S to T, well, assume all edges were positive in the beginning. All edges cost were positive in the beginning. So, for example, 1, 2, 1, 3. If we push one unit of flow, there will be 4 negative edges, right? So now a negative edge with the cost -1 appears from the second vertex to S, from the third vertex to second one, and so on. And that's the problem, because the main routine of this algorithm is finding shortest paths, and negative edges do not allow me to run Dijkstra's algorithm. And Dijkstra's algorithm is faster than Bellman-Ford. And my goal will be to actually use Dijkstra's algorithm instead of Bellman-Ford. And so this algorithm becomes faster. By the way, now what is the runtime of this algorithm? Well, it will be time it takes for us to find the shortest path. So with Bellman-Ford algorithm, it's n times m times the value of the flow, which is not too bad, right? Could be worse. For example, if constraints are small, like the old topcoder where all constraints were 50, this would be enough if the value of the flow is not too high. Okay, so now I'd like to tell you on the details, first on the details of the implementation of this algorithm, and then on how to optimize this algorithm to use Dijkstra's instead of Bellman-Ford. Okay, so just using Bellman-Ford is not good strategy. I usually use an optimized version of Bellman-Ford, which is motivated by this. So remember, in Bellman-Ford, we calculate values dp of k and u. And we use it, if we have an edge from u to v, then we update dp of k plus 1 and v. Right, so we add one more edge, and we use this edge, and maybe the distance to that vertex that uses at most k plus 1 edges, it's smaller than it was before. Actually, we don't usually use the first dimension at all, right? This is the textbook version of the Bellman-Ford algorithm. In reality, you don't use the first dimension k. You just use the same array. And it can be proven that in the end we'll get the same, even though intermediate values of this array, of this two-dimensional array and one-dimensional array, can be different. Okay, so let's use the version with two-dimensional array first. So I'll get those back. Okay, so assume on the previous step we updated k minus 1 u and k v. On each step, for each k, we'll do approximately the same, right? So we run through all possible edges, and we update distance to this vertex using distance to this vertex plus the cost of this edge. Well, what if we did update this on the previous value and this didn't change? So if this is equal to this one, then we don't need to do this update. Right? So for example, if I know that the distance to vertex u using 3 steps is 100, and the distance vertex u using 4 edges is also 100. Well, I did all the updates when k was equal to 3 with distance 100. Should I do these updates with 4 edges? Since we're going to find shortest path to the end and not with some fixed number of edges, this means that we should not just don't bother updating edges from u since this distance wasn't changed. So it only makes sense to update outgoing edges of this vertex when we have the new known best distance to that vertex. So whenever we update the distance to that vertex, we should somehow remember that on the next step, we should update all the outgoing edges of that vertex. And this is the main optimization that we'll use to have a better Bellman-Ford algorithm. Its worst case, it's still the same. It will be a little harder to detect negative cycles, but it's really useful, especially for specific networks like the ones we built for mean cost problems. Okay, so we'll use Q. The same as in BFS. Whenever we find some new vertex that was not visited, we put it in the queue. Here, when we find some new known best distance to that vertex, we'll put it into the queue. So if dist of u is updated, we put u into the queue. And to avoid putting the same vertex into queue multiple times, we'll keep track of which vertices are in the queue right now and which are not. So, and the pseudocode would look like this. So we'll have queue. We'll have this array, which I call in queue. So just a Boolean array that tells us for each vertex whether it's in the queue or not. In queue. Again, we'll use distances, which are infinities in the beginning. And this is false. And this is empty. And then we run our BFS algorithm, BFS-like algorithm. We usually call that Bellman-Ford with a Q, so we don't do unnecessarily relaxation of the dynamic programming. And in practice, it's a lot faster than normal Bellman-Ford algorithm. So this is what you should use if you are solving a mean cost problem. Okay, so we put the starting distance. So the distance to that is 0. And we'll say that it's in queue. And we put it in queue. So now we have our BFS loop. While the queue is not empty, let's take the first vertex out of it. While queue has at least one element, we take some elements, let's call it U. And then we look at all outgoing edges. If we update the distance to some vertex, we check. If it's in queue, we don't need to do anything. Okay, it has updated distance, but doesn't matter. It's kind of similar to Dijkstra's algorithm, right? So, but instead of priority queue, I use normal queue, and some vertices can be put into queue multiple times. So for UV in the graph, I take this, I compare distances. So first of all, I have to check if this edge is unsaturated, right? So I'm working in the residual network, and I must only search paths that have unsaturated edges. So if f of UV is less than C of UV, and distance to the end vertex, to V, is greater than distance to the vertex U plus the cost of this edge. Then we update distance V equal to this value, and if it was not in Q before, we put it into Q. So dist of V set to what's there, and if not in Q V, then add to Q and set in Q flag to true. And here, when we remove the vertex from the queue, we'll have to mark it as false. Add V to Q. So I got lazy and hid some snippets of code that should be there, but I think that you get the point. Okay, so there is one more thing. We need to actually restore the path. Right? We don't just need to find the shortest distance to the end vertex. We also need to find the path itself. So to do that, we do it as usual. We also have to store for each vertex not just the distance, but the distance and the previous best vertex or the previous best edge that leads to that vertex. So I'll call it this array prev. For now, will be filled with nulls. And whenever we update some distance, we also set I store edges in this array. So because there can be multiple edges between two vertices, I need to know which edge was the one that I need to update. So previous of v set to this edge uv. Or however you should call this edge. Right? So here you are iterating over all edges in the adjacents list, and you are saving this edge for UV. And now, when you've finished all this processing, by the way, you cannot stop when you put the last vertex into the queue, because it can be put into the queue again with the smaller distance. So you cannot just stop, like in Dijkstra's algorithm, you're sure. So when you pull the vertex from the queue, from the priority queue, you know that it has the smallest distance already, and the distance is true. Here you don't know that. So here, when you pull the vertex from the queue, you might be pulling that vertex from the queue again 100 steps later with the smaller distance. So you have to do all the possible iterations here. Okay, so that's the variation of the Ford-Bellman Ford algorithm that I use, and usually worked well. Okay, so let's have an 8-minute break, and we'll get back to using Dijkstra's, learning about Johnson's potentials, and if we have time, we'll discuss the Hungarian algorithm and some examples of the problem we can solve with this. so let's start. Okay, so let's start for now, and then the others will be back. So now I'll talk about how to turn, what do we need to modify so that we can use Dijkstra's algorithm instead of Bellman-Ford. And for sparse graphs, that's a great improvement, right? So it's big O of n times n to big O of m times log n. If we use Dijkstra's, or mn to n squared plus m. If we use the Dijkstra's algorithm without a heap, but with just a normal search. This is good for sparse graphs. This is good for dense graphs. Okay, so what I want to discuss with you is Johnson's potentials. You might have heard about Johnson's potentials in context of Johnson's algorithm that allows you to find all shortest paths between all pairs of vertices, even if there are negative edges. And it works like this. So there is a function phi that assigns a real number to each vertex. And our cost function is modified. So the cost of this new edge, the new cost of this edge, so W prime of U and V, is the alt cost. Now let me think. Plus phi of U minus phi of V. So there is a potential function that modifies the edge cost, and we're looking for such a potential function such that all edges become non-negative. Our goal is such that this new potential function is non-negative for all possible edges. If it is, if we can find such potential function, then we can use Dijkstra's algorithm. Well, we'll see why we can use it. And it turns out that if there are no negative cycles, that such function always exists. Well, it's easy to see that if there is a negative cycle, then such function cannot exist. So if there is a negative cycle, if a negative cycle exists, negative cycle C, then what is the cost of this cycle? Well, it's negative. Right? Well, what is the cost of the cycle? Well, it's cost of the first edge, U1, U2, plus the cost of the second edge, U2, U3, and so on. And in the end, we get UK, U1. So the sum of costs of all edges. Let's see what happens when we consider our modified cost function? Well, it's W for the first edge, U2, plus the potential function of the beginning, U1 minus phi of U2. So this is the new cost of the first edge. So what's the new cost of the second edge? It's old cost, U2, U3, plus the potential of U2 minus the potential of U3. And you see that the potential of U2 is cancelled out. And the same for the third edge, U4, 3U4 plus the potential of U3 minus the potential of U4. This way, phi of U3 is cancelled. And for the last edge, we'll cancel out the potential of. Basically, the potential function of each vertex is added once for the first edge and subtracted next for the second edge. So it's cancelled out. So it's the same as the old. So for the cycle, the new cost of the cycle is the same as the old cost of the cycle. And since this was negative, and our goal is to have all non-negative edges, then this cannot be non-negative. So if the total cost of the cycle is negative, we cannot have all non-negative cycles, non-negative edges on this cycle. Okay, turns out that if there are no negative cycles, then such potential function always exists. Phi exists as there are no negative cycles. There is a potential function as long as there are no negative cycles. We already proved it in one direction, right? So if there is no negative cycle, then such potential function cannot exist. Now let's prove it the other way around. If there are no negative cycles, then this potential function can exist. Well, let's define this potential function as. So we have our graph G. Let's create a new artificial vertex. Let's call it S. It's not the same as we have in flows. And draw zero cost edges to all other vertices. So after we do this, let's find all shortest paths from this vertex S. And we'll define phi of u is as the distance from S to U. So we find all shortest distance. There might be some negative edges, so that's why some distances, well, all distances are 0 or less, right? So the distances are at most 0 because we have a 0 edge from S, but they might be negative since there might be some negative edges, but no negative cycles. Since there are no negative cycles, then the distances are well defined. Okay, now let's see why this is true. So now we would like to check that for each edge from U to V, the new cost function is non-negative. Well, let's just write the expression for this cost function and check. So we want to check if old cost function of this edge plus distance from S to U minus distance from S to V is greater than or equal to 0. So I just expanded the expression here and substituted phi of U to be distance from S to U. And it's the same as distance from S to U plus the cost of this edge should be greater than or equal to distance from S to V. And this is the fundamental property of shortest path, right? So S, we can imagine this edge from U to V. So we have the shortest path here, and we have some other shortest path from S to V. Well, on the left part, we have the cost of some path from S to V, and on the right side of this equation, we have the length of the shortest path from S to V. So this is some path S to V that goes through vertex U. Maybe it's the optimal one in the case the new cost of this edge will be 0. So this is some path from S to V, and this is the shortest one. And of course, the cost of the some path will be greater than the cost of the shortest one. So this is why Johnson potentials always exist if potential function always exists if there are no negative cycles. So if there are no negative cycles, we can find Johnson's potentials and find phi. Well, what happens to the shortest path? Well, maybe if we modify the edge costs, the shortest path in the new graph will not correspond to shortest path in the old graph, right? But it turns out that for every 2 fixed vertices, so for like S and U, if we have some path P from S to U, the length of this path, cost of is only changed by a constant. Only depends on S and U. To be precise, W prime of P is the old cost of P plus the potential function of S minus the potential function of U. Well, why is that? Well, the proof is similar to when the cycle stays. But two terms here will not cancel, right? Because it's not a cycle, it's a path. It works, I think. Well, why is that? Well, it's the cost of the first edge plus phi of S minus phi of U1 plus the cost of the second edge plus phi of U1 minus phi of U2 and so on. And again, all the intermediate terms cancel out, and the only thing that's left is phi of S minus phi of the last vertex. And it doesn't matter what the path looks like, and the only thing that matters is all paths between S and U that have their costs changed by the same constant. So if we find the shortest path from S to U with the new cost function, it corresponds to the shortest path from S to U with the old cost function. And it turns out that if we use the potential function, the shortest path, the new shortest path will be the same as the old shortest path, but with this term. Okay, so how do we find potentials? Well, we can explicitly add this vertex S and just run for Bellman-Ford algorithm. But turns out we don't need to explicitly add this vertex. We can just initialize the array distance to all zeros this basically corresponds to doing the first iteration of the Bellman-Ford algorithm. So we can use Bellman-Ford, initialize this to every vertex to be 0 in the beginning. And in the end, we get the potential function. Okay, so now we learned about the potential functions, and now we need to apply them to mean cost algorithm. Right, so what we need to do is to keep updating the potential function so we can use Dijkstra's again. So the outline of the algorithm will look like this. If all edges that you have are positive, that's also the case, then you don't need to do anything, right? So you can just initialize your potential functions with all zeros and it will work. Our goal for potential function is such that there are no negative edges. So if there are negative edges, we'll find the potential function. If there are no negative edges, you can just use it as 0 and don't write any additional code. And then find the shortest path using Dijkstra's algorithm with the new modified cost function. Then update these potentials. Because after we found the shortest path, we get negative edges. Right? So we found the shortest path from S to T. And after we push a unit of flow along this path, we get reverse edges, which can be negative. Right? So there are now reversed edges with non-zero residual capacity that have negative cost. That might have negative cost. And now we have to somehow fix it. Find the shortest path. With Dijkstra's. And this is the A and this is the B. Update potentials. Okay, so how do we update potentials? I think every other step except the last one is clear now, right? So now we need to learn how to update potentials so that we can use Dijkstra's algorithm. Okay, so let's see. Where can negative edges appear? So negative edges can only appear along the shortest path that we just used to update. Well, since we use Dijkstra's algorithm, we don't just find the shortest path from S to T, but we also find shortest distances to all the vertices. Right? So I don't think there is a shortest path finding algorithm that only finds shortest path from S to T and doesn't find any other distances along the way. That works in general, right? Of course, there is A star and there are some heuristic algorithms that can find shortest distance from S to T without finding the shortest distance from S to any other, but for general graphs, I don't think there is an algorithm. So, turns out that the new potential function, phi prime of u, should be updated as phi prime phi of u plus the distance from S to u in this residual network. Well, why is that? Well, for the same reason this distance function worked at all. Right? So we can imagine that our initial potential function is 0. Right? So we have our potential function and we just change all edges weights to the new one, and we just forget that there were all old costs at all, right? So this we can consider to be 0, and this, well, let me tell you why do we use this at all. Well, because, well, suppose the distances were like this, 4, 6, 10, 13. And now we want all reverse edges to be non-negative. Well, it's hard to make them non-negative. Let's at least try to make them 0. So now all the reverse edges on this shortest path appear. We would like to make them 0. In the worst case, there is still a forward edge and the reverse edge on this path. And since their costs are negatives of each other, and we want to make them non-negative, we'll have to make them both 0. Right, so assume that this had a very large capacity, like 100, and we pushed 5 units of flow. So now the remaining capacity here is 95, and the remaining capacity here is 5. Well, but these two edges are well, these two edges are the reverses of each other, right? So they should have opposite edge costs. Well, and we want to have all edge costs non-negative. So the best we can do is to make them all zeros. Well, how do we make them 0? Well, we'll have to assign potential here to be 0 and the potential here to be 4. So before that, the cost of the edge was 4. Now it becomes 4 plus 0 minus 4 is 0. And the reverse is minus 4 plus 4 minus 0 is also 0. So this way, when we update potentials in this manner, all the edges on this shortest path are the same. And we can prove in a similar way using that. Well, using that initial proof that all other edges are still safe too. Right, so all the reversed edges that appeared on the shortest path are good because they become zeros. And all the other edges, they might become less, but they will still be non-zeros, will still be positive due to what we discussed on that board. Okay, so update potentials is just new potentials for each vertex is old potentials plus the distance that we found using Dijkstra's algorithm. Distance from S to U. So that's how we can use Dijkstra's algorithm. Right? So we use an additional potential functions, and we keep updating this potential function so it helps us to maintain non-negative edges. And we update these potential functions by just taking the old potential function and adding the distances that we found on this step. Yes?
Is this S that S or the S from the flow?
S from the flow, yes. Well, we don't need that S, right? So that S is only needed for like theoretical proof. Well, usually the source is called S, so there might be some confusion. Okay, so that's it. And so the total algorithm works in big O of, well, this flow times Dijkstra's instead of 4 Bellman. Let me call it M log n plus, maybe plus M times n. If we have negative edges in the beginning, edges with negative costs, so we need to find the initial potential function. If all edges are positive, which is often the case, then we don't need to run for Bellman on the first step. Then we can just initialize the potential function to be all zeros. So basically save the initial edge cost to be the same. And then we will update potentials as we go after each Dijkstra. Or it's value times n squared plus m if the graph is dense. So if there are a lot of edges, then it's preferred to use Dijkstra's algorithm without heap, since it's slower than just the first version that you probably learn, where you find the minimum, the vertex with the minimum distance in linear time, but you update each edge in constant time, which is a plus. Okay, so let's see what we can do with mean cost flows. The most famous, probably, application of the mean cost flows is the solving the assignment problem, which is the same as minimum weighted matching in bipartite graph. So yesterday we talked about just finding the matching using flows. Now we can solve the weighted matching, and I think we have enough time to discuss the Hungarian algorithm, which is not that complicated. Okay, so weighted assignment problem. So the assignment problem is like this. You have let's say an n by n table with numbers, and you have to select, basically for each row you have to match some column, or in each row and in each column you have to select exactly one cell, such that the sum of the cells is as low as possible. So you can choose this one, and the sum of cells should be minimized or maximized, depending on what you solve. Okay, so that's the assignment problem, and it can be viewed as finding the minimum weight matching in bipartite graph. So if we imagine this as a bipartite graph, so we have vertices corresponding to rows on the left, vertices corresponding to columns on the right, and the cost of this edge is Cij. So now we would like to find the matching in this graph. Usually this is formulated as if we have a complete bipartite graph with n vertices here and n vertices here. If there are not, if some edges are missing, we can just put some large values, some infinities here and there. If two parts are not the same, we can add fake vertices to the other part. If the number of vertices in some part is a lot larger than in the other part, it's better to specialize the algorithm, but this will still work. And as before, we create an artificial source and the artificial sin vertex. We draw edges with capacity 1 and cost 0 to all vertices on the left. We draw edges with cost Cij, and again, any capacity you want. You can have infinite capacities. And again, from the vertices on the right part, we draw edges with capacity 1 and cost 0. So that's how you solve the assignment problem. Let's take a look at what is the runtime of this problem. Well, we can make all these values non-negative. For example, by finding the minimum value and adding it to all the values in the matrix. In this way, if the number of rows is the same as the number of columns, then the cost of any matching is increased by this minimum value times n. So if we find the minimum matching, and as I said before, if all Cij's are non-negative, then there are no negative edges and there are no negative cycles. So we can solve this using this version with Dijkstra's. So initially, we can initialize potentials as just a constant 0. Then n times, since the maximum flow value here is n, right? There are n units of flow that we can push. N times, we run Dijkstra's algorithm. And since the graph is dense, since we have in order of n, since we have 2n plus 2 vertices and n squared edges, more than n squared edges, this graph is dense, so it's preferred to use the version that works in n squared plus m. So the total runtime is big O of n times n squared plus m, which is the same as big O of n cubed. And as we see, maybe if you know, the Hungarian algorithm that solved the assignment problem, which is a specialized algorithm for solving the assignment problem, it has better constant, so it will work faster than if we run min cost algorithm for this graph, but the asymptotic runtime is the same. So the Hungarian algorithm also solves the assignment problem in big O of n cubed. And again, we can use some different approaches. So for example, we can say that we can choose 2 cells in each row. So for example, we just modify this to be 2 and so on. And we have some, today we have a contest dedicated to flows. So there will be flows, there will be min cut reductions, and there will be assignment problem, and there will be min cost flows. And I hope there is enough variety today that even if you knew min cost flows and flows before that, you'll find some problems to be interesting. If not, I have some more problems and I can add them during the contest. Okay, so now let's talk about the assignment problem. We have about 40 minutes. I think that's enough. Let's talk about the assignment problem and the Hungarian algorithm to solve this problem. I need some more colors. Okay, so as I said before, The assignment problem is that you have an n by n matrix, and you have to and by n matrix, you have to choose some cells, exactly one cell in each row, exactly one cell in each column. So basically you have a perfect matching between rows and columns, such that the sum of those cells is maximized. First, some trivial observations. We can do plus x for all numbers in some row or in some column, and the answer doesn't change. Well, the cost of the matching changes, but the matching itself stays the same for all numbers in any row or any column. And this doesn't change the structure of the answer. It changes that the answer is now larger by x, or if x was negative, it's smaller by minus x. But the structure of the answer doesn't change, right? If some perfect matching was optimal, then it is still optimal. Okay, so that's the first important observation that we will use a lot during the algorithm. And the second observation is, well, let's assume all values are non-negative. We can achieve that if we add the minimum one in each row, for example, or if we find the minimum value in the entire matrix and add it to all rows or all columns. We can make Cij greater than 0. Okay. Well, if there is a perfect matching, well, any perfect matching now costs non-negative. Any cost, well, cost of any matching is non-negative. Well, if there is a matching that costs exactly 0, this one is optimal. Of course, there is no negative matchings, and if we have some matching that costs 0, then it must be optimal. Matching with cost 0 is optimal. Matching or assignment, which one you like more. So matching with cost 0 is optimal. And the goal of our algorithm will be to subtract something from some rows, subtract something from some columns, or maybe add some values, such that we'll keep all values non-negative, but there is a matching that costs 0. This means that this one is optimal. Okay, so we'll go row by row from top to bottom and build our matching first for only the first row, second for first and second row, third for first, second, and third row, and so on. So we'll add rows one by one. Okay, now let's begin. So let's consider the first row. Suppose that we already made it so all elements are non-negative. You don't need to do that explicitly in your program. If we have time for implementation, I'll show why this is the case. So how do we make the matching here? Well, let's find the minimum value in the first row and subtract from the first row. So suppose here is the minimum value. Let's subtract it from the row, from all the numbers in this row. Minus min, so this becomes 0. And maybe there are some more zeros, but there is at least one 0 now. Let's mark this 0 as chosen. So our goal is to choose some cells in each row, in each column. So for the first row, we'll say that we have chosen this cell. This is 0. Remember, our goal is to build a matching entirely on zeros. So this is the first step to building that matching. Okay, we're done with the first row, right? So for the first row, we have a matching that only uses zeros. And the only operation that we did is we subtracted all the values in the first row. We subtracted minimum value from all the values in the first row. Okay, let's do the same for the second row. So we have this. So we have the second row. Let's find the minimum value. Suppose it's here, x. So we find the minimum value in all the possible columns. We take this, we find this minimum value, and we subtract this minimum value from all the values in this row. So this becomes 0, and maybe there are some more zeros, but this becomes 0. So let's mark it as used for this row. And go on. Is this it? So we just add the rows one by one and find the minimum value, subtract the minimum value from all values in that row, and just mark the minimum value, which is now 0, as used. Do we need to do anything? Yes. So the problem is when the column was already used. So let's assume that happened on the second iteration. So for example, well, the values in this column are so low so that every row wants to use them. Okay, so this is 0. Okay, we cannot use this 0 and this 0. So that's bad. Now, okay, so for now, we will save that this row wants to have the 0 in this column. Okay. So we can also draw this kind of a reminder. So there was a conflict, right? So this row found a 0, but this column was already used in this row. So we draw this kind of an edge from this row to this row. This means there was a conflict that this row wanted a 0 in the same column that was used by the first row. Okay, now we'll go ahead. So before that, what we did is we found the minimum in the entire row. Now let's find the minimum in this area. So we have 2 rows except for this column. Let's find the minimum value in this entire area. And then we want to subtract the minimum value from all the values that are colored blue. So what do we need to do? Well, let's suppose the minimum value is here. So the minimum value x is somewhere here. So we need to subtract x here. X for the first row and x for the second row. We only want to use operation subtract something from the row or subtract something from the column. We cannot say that we need to subtract all the values from the blue area, since it's not a valid operation, right? So, because if we subtract values from this area, the matching can change. So we can only use operations subtract something from row or subtract something to column or add something. Okay, so we'll subtract x from the first two rows. But now what is the problem? Yes, so there were two zeros, they become negative. So what can we do to fix that? Fix it? Yes, we can add back to this column plus x. So now these zeros are still zeros, and all the values here are decreased by x. Well, some values here are increased by x, but that's not a problem, right? So they were already non-negative, and they are still non-negative. Okay, so now we have two cases. So first case, we found the minimum, and it was on the first row. So now this is 0, right? Because we subtracted x everywhere. So now this is 0. Now we'll say that the first row has now chosen this column instead of the conflict column. And we forget about this 0. Now the first row has two zeros. This one, and we choose this one, the one that's not in conflict. And we choose this value for the second row. And there's another case where the minimum value was in second row. Then okay, let me draw another example. So we have two rows. We had a shared 0 in this column. And the next 0 that we created was in this row. So what do? We keep this 0 as is. And we say that we choose this 0 and this 0. And this is valid matching, right? Each column is used at most once, and each row has exactly 1 0 so far. Okay, so what happens when we add one more row? So again, we find the minimum in that row. So suppose it's here. Find the minimum x. Subtract x from the row. This becomes 0. If this column is not used, then we just mark it as used and go on. And if there was a conflict, for example, with the first row. So for example, this column has 0. What do you think we need to do now? So we created a 0 in the third row, and it's in conflict with the first row. What do you think we need to do now? Well, again, let's remember that there was a conflict, that third row created a 0 in the column that was already occupied by the some row. So we'll save this edge. And then we will try to find the minimum in the remaining area. So we have two rows except one column. Except one column that has a conflict. So we use this area. And we find the next minimum. It might be in unused column. So somewhere here. So if it's here, Then again, we subtract x here, we add x here. So the zeros are untouched, and all the other values are decreased by x. And all the values in this column are increased by x, but we don't care about it. So if it's here, we just forget about this 0 and make 0 here. If the minimum is here somewhere, we forget about this 0, make x here, make the 0 as the chosen one in the first row. And there's one more bad case. We can use one more 0. Right? So we still have a forbidden column, and we can choose the 0 from there. So assume that it goes from here. Okay, so now we have a new situation. Now we have two conflicts, right? So the conflict in this row and conflict in this row. Let's draw one more edge that says, okay, we wanted to choose this 0, but the second row already had a chosen 0 in that column. So we draw an edge from the second row to the first row. This is, if you know Kuhn's algorithm for finding the matching in graph, this is kind of similar. So now we're going to try to find this augmenting path in kind of a bipartite graph where the left part is rows and the right part is columns. Okay, so now we have two restricted columns. And 3 rows that we choose from. So now our next step is we find the minimum value in these 3 rows except for these 2 conflict columns. Now, if we find the minimum, if it's on the last row, we just change this 0 to the last row. If it's on the first row, we change this 0 to the first row and we keep this 0. And if it's on the second row, we change this 0 to that minimum that we found. We keep this 0 and we keep this 0. Okay, so now I think we will not go with 4 rows. I think we're ready to generalize the algorithm. So let me write some pseudocode and we'll discuss the details of the implementation to make it faster. So we still have some kind of expensive operations where we need to subtract something from the row or finding minimum can be done more efficiently. But we don't need any complicated data structures to do that. So the pseudocode will look like this. I'll leave some place for defining which arrays I need. So I'll go for I from 1 to n. So I'll add rows one by one. Okay, so now I need to do this kind of loop. So in the beginning, I have 1 row and 0 forbidden columns. If I find a conflict, I'll have 2 rows and 1 forbidden. So let's say we'll have array used of n that tells us which columns are forbidden. And we also store this kind of edges. We haven't used these edges yet, but we will use them to resolve conflicts. So for example, if in the end we found that the minimum element is contained in the second row, we will need to change the 0 chosen for this row, then for this row, then for the first row, then for the third row. So we'll use these edges to go back to the first row and fix all the conflicts along the way. Let's say parent n. Parent, let's call it conflict 3. Okay, so I need these two values. And I'll also need the minimum in each column. So the data structure I will use to find minimum in this part, in this blue part, is for each column, I will find the for each column, I will keep track of what's the minimum value and what's the row of that minimum value. So min is min value in each column. And something like min pos, which is the row where that minimum value is achieved. I think that's it. Okay, so now we have our current row, which is row I. We'll try to add this row, find the minimum element in all the chosen rows except for the forbidden columns, and then maybe fix all the conflicts and go to the next row, or we add one more row to the set of blue rows and forbid one more column because there was a conflict. So while true, always a good start for an algorithm. So we want to add this row, which we defined as current, and find the minimum position. So for j from 1 to n, if first we'll have two parts. So we go over all columns. First, we update the min array and min pos array, and then we check the minimum value if it was not a used column. So if not used j, so if, well, I'll have a matrix, let's say A large of I and j. If A of I and j is less than min. And of course, since we're looking for minimum values, we should initialize this with very large values. So with infinities. Min j. Then we say that min j is A of I and j. But also min pos of j, so that the row, sorry, not I. Here we should only look at the current row. And min pos is equal to current. So first, we updated the values of min and min pos. Then we would like to find the column with the minimum value. So to do that, I need some variable. So min col is -1. Well, let's say let's -1. So if min col is -1, or that's just the code to find the column with the minimum value, the non-used column with minimum value, or min of j is less than min col. Then I say that min col I set to j. Okay. So that's basically the half of the algorithm already. So we just find, we maintain, for each column, we maintain the minimum value in that column in all the used rows. So in the beginning, we'll only consider the last row. If there was a conflict, we add another row but exclude one column. So now we'll find the minimum in that area, and so on. Okay, so that's it. Now we need to check if minimum column is used or not. Does minimum column have a pair or not? Well, to do that, we will need to somehow maintain which columns are assigned to which rows and the other way around. So let's say that I have match row and match column. Well, match row says which column this row assigned to, and match column says tells me which column this assigned to. In the beginning, we need to assign some non-existent values to them, say -1s. Okay, so now I need to check. So I have this 0 in the new column. Well, it's not 0 yet. I need to subtract something, right? So I found the minimum place, and I need to subtract that minimum value from all the blue area. Well, how do I do that? Well, I need to go over all used rows and subtract it from them, and I need to go over all used columns and add this value to them. So should I continue on this side? Okay, so this is the first part, and this is the second part. So now I need to subtract this minimum value from all the... Well, it's time to tell how I actually subtract. So I will not actually modify matrix A of I and j. Instead, I'll have two additional arrays. I'll call them row and col. So row of I is the amount that I need to add to the ith row to the actual matrix. Is the add, what to add to the ith row. And the same for column. Col I, col j. Okay, so now some things need to change here. Since I don't modify the matrix A of I and j, here I need to add plus row I plus col j. So since I store changes to my matrix somewhere else, I need to add them each time I look at some cell in my matrix. So I look at here and at here too. Yeah. And now subtracting something from a row becomes easy. I'll just say row I minus equal x. So for now I want to subtract from all used rows and add to all used columns. I'll just say that if I have a used column, J, I will add to it, call it J, add X. Well, why was the column used? Well, the column was used because the corresponding row, so some cell in this column was chosen in some row, and that means that the matching row for that column should be subtracted. We should subtract x from the matching row to that column. Sorry if it's a little bit unclear. So we need to subtract. So for example, if we have 3 rows and 2 columns, well, we need to do plus x in those columns and minus x in all these 3 rows, right? So in the beginning, we had this chosen cells. So this cell was chosen and this cell was chosen. So this means that the matching row for this column was the first one and the matching row for this column was the second one. So what I'll do is I'll iterate over all columns. I'll check if this column was used. Then I'll add to this column and I'll subtract from the matching row. So I'll subtract from the first row and the second row, and then I'll manually work with the last row since nothing was assigned to this row yet. Call J, we add x, and row for the matching to that column. And then we need to manually subtract the last row, which has number I. Okay, so that's how we decreased all the values in the blue area by x. And we left this zeros non-touched, and everything else is still non-negative. It might increase, but it's still non-negative. Okay, so now, and of course the x is mean value of min col. So we found the minimum column, and then we subtracted everything. So now is the time to check. Well, we found the new minimum column. Is it used or not? Does this column have a matching row or not? So let's check the optimistic case in case it's not matched to any row. So if match column for min column is -1, then we just need to match it, right? So we'll just say that match call for min col. Well, what is it? Well, we need to find the row where this 0 was actually created. And that's why we need the min-pos array. So min-pos array stores the row for each column. It stores the row where this is. This is as small as possible. I might messed up somewhere in the min-pos arrays. I think we still need to modify this min array, right? So since we subtract from the blue area, every column in this blue area has this minimum subtracted. We subtract x from the minimum in each blue column. So if the column was used, we actually add and subtract. And if the column was not used, I'll just subtract x from the minimum in that column. I think that's what I missed. Okay, so if the matching column, if there was no matching row for that column, I need to match it. So I'll just say that it's min pose of min col. And then I need to go along these edges and fix all the conflicts along the way. So while cur, well, let's do it the other way. While cur is not I. Well, I have this edge from cur to parent of cur in this conflict tree. And basically I need to take what was matched, what column was used for this row, and instead use it for this row. Or the other way around, sorry. I need to take what column was used for this row and use it for this one. I'll just leave it in words, so you'll have something to figure out for yourself. So, match parent of current row to column formerly used by this current row. And then we go up this tree. Current equal to parent of the current row. So this is how we fix all the conflicts. And then we basically added one more 0 to our current matching and we're done. So we break out of this while true loop. Otherwise, it's a bad case. So we just mark some column as used and change the cur variable. So actually the second case is easy. So we'll say that the used of min col is true. And just say that the current row is now the one that was matched to this minimum column, which is not -1, as we checked. Match column of the minimum column that we found. And we continue this while loop. So basically, by doing this, we added one more row to the list of the rows we're considering now. And we need to somewhere we put the parent link, right? So parent of what? Min parent of this thing cur we set to be what? We need to find what row it's in conflict with. So we need to find what row has this matching 0 already. Parent of cur is min pos of min call. Okay, so well, there are a lot of like implementation details of which arrays how we should use these arrays, but the essence of this algorithm is, I think, pretty easy, right? So we add rows one by one, we make one more 0 in the next row, then we try to put the matching into this row. If we are good, then we continue, and if we're not good, then we find the conflict. Now we use 2 rows, except for 1 column. We find the minimum in that area, and so on. So we add rows one by one until we can rebuild this entire matching. And the time it takes to execute is, okay, so we have this for loop. It's of n. This while loop will execute at most n times. Well, at most I times for the ith row of I. And each iteration of this while loop works in linear time, right? So we look at all possible columns, then we look at all possible columns again, and then we do something. So the total time is n cubed. And that's called the Hungarian algorithm for solving the assignment problem. Okay, so it's better if you try to understand the algorithm and not just copy any existing implementation, but at least try to implement it once yourself so that you understand how this algorithm works. And if you don't, I'm here to help. So I think that's it for today. Today we have a flow selection, the compilation of flow problems. Some problems use a Hungarian algorithm. Some problems use min cost algorithm. Some problems require a normal flow algorithm. And sometimes it's hard to distinguish between the min cut problem and the min cost problem, but I hope that's the skill that you will learn today. Okay, so any questions? Okay, so if you want, you can ask me questions in private, but for now, the lecture is over. Thank you.